Give me 1 second. Let me. Okay. Just a second to find out which file to share. Okay. So I'm guessing everyone is able to see my screen with the Word document. Okay. So ideally, I'd hope to write down as we were speaking, but unfortunately my tablet was out of battery and I did not plan ahead and charge it. So, but I do have some notes that I prepared ahead of time. So I think we can still go through that and still talk about this. So let's continue from yesterday's discussion of low power wide area networks. So we started talking about the concept of long range communication. And if you guys remember, we talked about few wireless technologies, Wi-Fi, cellular network, Bluetooth, and we talked about some of them having a longer range than the others. Just a quick sanity check. How many of us remember where the cellular network, why cellular network has long range? Can someone unmute themselves and say what they think the answer is?
Due to frequency.
Because of frequency, right? So cellular networks operate at a much lower frequency. And as we see here in this first page too, your path loss we lose path energy as we go farther and farther. At the same time, it's also inversely proportional to wavelength. In other words, it's directly proportional to frequency. So the higher the frequency, larger is our path loss. So we briefly talked about free space path loss, and we realized we talked about how we want the receive power to be high if we want the range to be long. And if our receive power has to be high, we want the receive power is the transmit power minus path loss. You can ignore some of these constants. Like I mentioned, this was for a different meeting, so different session, but I think many of the contents we can still reuse. So if we want to go for longer distance of communication, we want our path loss to be smaller. So we prefer lower frequency. So yeah, if we just, one of the questions in yesterday's session was which frequency would give us the lowest path loss, right? And you can see that path loss of a 28 gigahertz signal would be much higher than 5 gigahertz, which would be higher than 2.4, and that'll be higher than 1 gigahertz and so on. So all of this to say, when majority of the technologies that are focusing on long range communication operate in something called sub-gigahertz frequency. All that means is the carrier frequency of your communication of the transmitted signal is going to be below 1 gigahertz. So if you want to go longer and longer distance between your sensor and the nearby base station, we want to operate at a gigahertz, at sub-gigahertz carrier frequency. And that will help us reach long distances. And one of the frequencies that's most popular in low power wide area networks is 915 megahertz in the northern United States, because it's an unlicensed spectrum. Once again, going back to licensed and unlicensed, I'll quickly give an intro to that. The frequency that we use for Wi-Fi, which is 2.4 gigahertz, which is also the same frequency for Bluetooth, Wi-Fi, the microwave frequency that's in our homes. Microwaves also operate at 2.4 gigahertz. They're all under the category of unlicensed spectrum. Under the government's regulations, anyone can use those, send and receive in those frequencies, as long as we follow certain rules of transmit power and so on. Whereas cellular network, they pay for the carrier frequency that they operate in. For example, in the United States, the carrier frequency that AT&T has purchased cannot be used by a different carrier such as Verizon or T-Mobile. And same with any country, right? The 5G spectrum, for example, is being auction for licensing by different companies. So each company owns a portion of, owns or leases a portion of the spectrum. Whereas there are certain ranges of frequencies that are unlicensed. So this 915 megahertz and the range of 902 to 928 megahertz, those range of frequencies are unlicensed in the northern United States. So that has become one of the most popular go-to carrier frequency for low power wide area companies. And the reason I bring this as companies is LP WANs or long range communication. Beyond research, it has gone into products now. And when companies are building products, they want to be aware of the cost for these licensing, cost for device manufacturing, and so on. So we now operate at 915 megahertz to reach long range of communication. But there are some challenges with going lower and lower frequency. So we can then ask, okay, 915 megahertz is unlicensed. Can I go further down if I want to go longer and longer range? What if I go further down to, say, 500 megahertz or 200 megahertz, 100 megahertz, and so on and on? The biggest challenges with that is the hardware aspects of it. Some of you might have studied in your communication courses where if we want to communicate at a particular frequency or a wavelength, our antenna's length should be proportional to a quarter or half of that wavelength. So when our frequency goes lower and lower, our wavelength goes higher and higher, right? So as the wavelength goes higher and higher, our antenna size has to be higher and higher as well. So if we go much lower in frequency, we want a physically large antenna. And if we think of sensors to be deployed in fields, we don't want large dish antennas to be placed out in the fields, disturbing the environment just so that we can sense, right? And that's true with our the devices that we carry as well. If we want to go lower and lower in frequency, our antennas have to be higher, larger and larger. And that's physically, it's cumbersome. And one of the reasons we choose an optimal frequency of close to 1 gigahertz is that we can still operate with a reasonable path loss, reach distances of few kilometers with an acceptable antenna size. So it's except for now that 915 megahertz is our carrier frequency. The next question is, how do we convey this information? Professor Suresh must have talked to you about different layers of networking in the last 4 sessions, I'm guessing. How many of us know which layer which is the layer where we start thinking about this carrier frequency, how we modulate that carrier frequency and how it is sent over air and everything? Which layer do you think is responsible for this? Once again, we have a few of us in here, right? So you can unmute yourself and answer. So there are layers starting from application, transport, network, link, and physical. Which one did you think is responsible for modulating the carrier signal and exactly sending deciding exactly what to send over the air?
Physical layer.
That's exactly right. The name itself goes with that too, physical layer. So physical layer takes care of how we physically transport message to bits to electromagnetic signals over the air. I won't spend a lot of time on how exactly we're going to modulate, but if you're interested in that, I think it's a really fascinating area of communication system, and it becomes a core concept in communication to know what all physical layer technologies exist. And if you're interested in doing more courses in that, ping me, I can point you to certain courses in CEG outside as well. But let's quickly go through what modulation does and how can we change the modulation so that we can go to longer distances. So I'm going to just revise some modulation quickly so that we can go talk about some advanced modulations that enables us to go long distances. How many of us here know what frequency shift keying, amplitude shift keying is? Just raise your hands if you're familiar with those names. It's okay either way. I just want to get a sense of how many of us know or not. I know that Okay, so it looks like I don't see many hands up. So I'm guessing the term modulation and how information is conveyed in electromagnetic signals and over the air is still relatively new concepts for all of us. So I'll have a quick run through that. So just the name frequency shift keying and amplitude shift keying, they refer to different modulation techniques. So like you pointed out, in the physical layer, we have we decide how an electromagnetic signal is sent over the air and how should one receive. And one of the key algorithms or key technologies in the physical layer is called modulation. So modulation is exactly is what decides how to map bits to electromagnetic signals. So although we keep talking about, say, when you're sending a message, for example, or let's say YouTube, if you're watching something on YouTube, you type the video that you want to watch, the name of that, and you send that name to YouTube server, and YouTube server sends back the video to us, right? So there are a lot of things happening in this whole pipeline, and some of that you might have already seen in the networking intro by Professor Suresh. So starting from the request that you have, which is say 1983 movie highlights. So in 1983 movie highlights, when you type those words, 1983 highlights, they are mapped to bits. And those bits are then mapped to, if it's a wireless connection from your phone or laptop, those bits have to be mapped to EM signals. And the EM signals propagate over the air, received at the base station. The base station then sends it back to the server. Server demodulates that information, understands your query, sends the video back, and the whole process is repeated. So modulation is the step where you map these bits to EM signals. So let's take frequency shift keying. And I have a crude example here, although it's a little more complicated, just to simplify what frequency shift keying does. Let's say your message 1983 highlights is mapped to 100 bits. And for ease of discussion, let's assume it's going to be alternating zeros and ones. So I have to somehow tell the receiver that an EM signal that I'm sending is mapped to 0, and an EM signal that I'm sending is mapped to bit 1, right? So if I have only bits 1 and 0 to send, I need two different ways of conveying to the other person that this is going to be frequency 1 and 2. And just like language, right? We have mapped certain characters and certain collection of characters to a message. So the way we move our mouth, the way we change our intonation, all of that corresponds to a sound, right? So what we do in our mouth for speaking is exactly what modulation does. How we are modulating the sound, the air medium between us and the receiver is analogous to modulation on an modulating an electromagnetic signal. So frequency shifting, like the name says, maps a bit to a particular frequency. Again, this is not how it's actually done, but a simplistic way of visualizing this could be that if I have an EM radio, and if I send 915 megahertz to convey bit 0 and 915.1 megahertz to convey bit 1, so one of them as bit 1 and one of them as bit 0, if you are the receiver radio, let's say, and you're listening to this signal, and if you heard 915 megahertz, you'll map it to bit 1. If you hear 915.1 megahertz, you can map it to bit 0, right? So if I have two bits, I want two unique frequencies to send over the air. Again, just to reiterate, this is not exactly how frequency modulation is performed, but a simplistic view of what frequency modulation could be is that we map a bit to a unique frequency. So again, in digital communications, we learn how to perform frequency modulation on a carrier signal. But let's say we want to send 2 bits once again. So how many frequencies do we need? How many unique frequencies do we need so that the receiver can understand, differentiate between bit 1 and 0?
2.
2, that's right. So if I want to send bit 1 or bit 0, I need 2 frequencies. What if I want to, and then there is a certain amount of time. So you and the receiver decide on a certain amount of time. For example, here, we all decide that at this point, I'm going to start sending something. And every capital T duration, I'll continue to send this message. And from T to 2T, I'll change. And depending on what my frequency is, I'll change it to a different message. So in this case, we both agreed that we are going to start here. And for a certain amount of time, I'm going to send a frequency corresponding to 0. And the next amount of time, I continue to send that frequency. So this T, capital T, we have to agree on that ahead of time. If we don't agree on that, you don't know I was sending this frequency 3 times to convey bit zeros again and again. So this capital T of how long I send to a particular bit, that's important to know. So that has to be agreed upon ahead of time. So that's called a symbol duration. So for a certain duration of time, I'm going to send a bit, and for a different duration, I'm going to send a different bit. But let's say now I have these 2 bits to send. So I'm sending 1 bit in this duration T. So what is the rate at which I can send message? 1 divided by this capital T, right? So my data rate would be 1 over capital T, because at every capital T unit of time, I'm sending 1 bit worth of message. Let's say now I want to send faster than this. I want to send 2 bits in the same duration. Using different frequencies. What can I do? Any thoughts? So you mapped 1 bit 1 or bit 0 to 2 unique frequencies. Now I'm saying in the same amount of time, I want to send 2 bits. What can I do? Take some guesses. Okay, let's say I give you 4 frequencies. What can you do with those 4 frequencies? And I'm saying I want to send 2 bits of messages with 4 frequencies. What can we do? I'm just going to put someone in the spot. Bhavya, what do you think we can do? If we have 4 unique frequencies, and I want to send 2 bits in time T. I'm not sure if you heard me, Bhavya. And it's okay if you say you don't know, that's fine too. Don't worry.
I mean, is there any criteria as to which 2 frequencies should be chosen to represent each?
Doesn't matter. Let's say I'm giving you 4 different frequencies, and I want to send 2 bits in the same time T. What can we do? So what did we do with 2 bits? We mapped bit 1 to 1 frequency and bit 0 to a different frequency. So I'm sure you all studied logic gates by now, right? If you can map, if you want 2 bits, then there are 4 possibilities that those 2 bits can take, which is 0, 0, 0, 1, 1, 1, and 1, 0. So there are 4 possibilities. If I map each of these possibilities to a unique frequency, then I can send one of these frequencies and the receiver will know exactly which bit sequence I tried to send, right? So let's say instead of mapping bits 1 and 0 to each of these frequencies, I had 1, 2, 3, 4 frequencies, and I mapped 0, 0, 0, 1, 1, 0, 1, 1 to one of these frequencies. And instead of in this same duration T, now if I send F1, my receiver will know that it was mapped to bit 0, 0 and not just 0. So now in the same duration T, we managed to send 2 bits. Let's extend that a little bit more. Now I want to send 4 bits worth of information. How many unique frequencies should I have at my disposal to send 4 bits of information in that one duration capital T? So think 4 bits, did I say 4 bits? Let's take 3 bits. I want to send 3 bits of information.
16
So
power
16 for what?
4 bits.
For 4 bits. And how did we get to 16?
2
that is
power
correct.
4.
2 power 4, right? So 4 bits would have 2 power 4 possible bit sequences. And each of those 2 power 4, if we map it to a unique frequency, we'll need 16 frequencies, and so on and on, right? So I think this would be a good time for us to go to our quiz and look at the first question. If you guys can make a note of this for your question 1, make sure you're able to answer that. So essentially the question is asking how many bits can we send if we have 32 FSK? So in this case, when I said 16 unique frequencies, we can call it 16 FSK. So that 16 represents how many unique frequencies you have. Let's say you have 64 unique frequencies. How many bits can you map to that with the help of that? There are 64 frequencies. 64 is 2 power 6. So how many bits can we send in the same duration?
6.
6 bits, right? So 6 leads to 2 power 6 combinations of bits. And then we are mapping each of those to 2 power 6 unique frequencies. I'm seeing a chat message. Okay. Yeah, 16. That's right. I'm just seeing your chat message. Sorry. If you guys can unmute yourself, that might be easier and quicker for me to go through. Okay. So if we have more and more frequencies, our understanding is that we can map more and more bits per frequency. But one of the challenges with more and more frequencies is that on the hardware side, we need to generate so many more frequencies. But that aside, when I told you about this center frequency of 915 megahertz, right? So there are only a range of 902 to 928 megahertz that are unlicensed frequencies, and of which there are government regulations on a range of frequency you can use at a particular time. So that would define the bandwidth of the signals that we can transmit. And we'll talk about I don't think we have enough time to talk about bandwidth and how that affects data rate and so on. But let's take for a fact now that you have limited bandwidth, limited range of frequencies that you can send. So if I tell you that you can only go in steps of 0.1 megahertz and you only have 1 megahertz at your disposal, then you only got 10 frequency steps, right? So there are in steps of 0.1 and you can only span 1 megahertz, which means I can only take 10 frequencies at a time. And log to the base 10, log to the base 2 of 10 would be 3 bits per symbol. So I think I keep using the word symbol. I'll get to that in just a second. So one of the challenges with the advantage of increasing the 16 to 32 to 64 FSK is that we can pack more and more bits into the same duration. But if we end up packing more and more, we have to start expanding on the number of frequencies that is given to us. And that would become the bottleneck on how many frequencies we can send. So the reason I started with FSK is that one, it's quite easy to follow, but it also led to the state of the art on long range wireless networks. So just to recap, if you have 2 FSK, you can send 1 bit per symbol, 1 bit with 1 frequency. If you have 4 FSK, you have 2 bits. If you have 16 FSK, you have 4 bits, and so on. And this time duration that I mentioned, within that time duration that the receiver and the transmitter agree upon, that time duration, whatever we are able to send, is called a symbol. So it's called a symbol duration. So what does 1 frequency represent is called a symbol. So in case of 16 FSK, 1 frequency maps to 4 bits, right? So the number of bits per symbol in that case would be 4. So the symbol duration would be the same across all of them, but the number of bits that is mapped per symbol would be different. So again, the number of bits per symbol, and therefore the number of bits I can send in a given time, is higher with higher order FSK. So this number is called the order of the modulation. But due to bandwidth limitations, we'll be limited by the number of frequencies that we can go to. Any questions so far? Okay, so I'll quickly mention a different modulation, which is called amplitude shift keying. So it's quite similar to frequency shift keying in the idea of mapping bits to something. In the case of frequency shift keying, we mapped it to a particular frequency. In case of amplitude shift keying, we map the bit to a particular amplitude of our carrier signal. So instead of sending, say, in the same duration, I send a particular frequency. Instead, if I send a carrier signal of one amplitude for bit 1 and a different amplitude for bit 0, that would be amplitude shift keying. Once again, I'm oversimplifying this. Amplitude modulation by itself is, or amplitude shift keying by itself is amplitude of the carrier signal. But let's now, just for understanding, let's take that the amplitude of your carrier signal, different levels of amplitude would be mapped to different bit sequences and so on. So one of the first methods that people started using was for long range communication was this frequency shift keying. And the reason for that is when you send these frequencies, right? If I'm sending one frequency versus the other, two different bits are mapped to these frequencies, the receiver can be sure that if I receive a particular frequency, this is bit 1. The amount of interference from others would impact frequency shift keying lesser than that of amplitude shift keying. So just think about the way we speak, right? If we just change the way our, if our communication is only based on the amplitude or the loudness of our voice, that can be interfered very easily, right? So if it's just about, if I'm just humming, let's say, and you're trying to guess the song that I'm humming without any words, just from the amplitude of my voice, even if someone is speaking next to me or there's a car driving by, there's a horn in the back, all of that will affect my hum, and therefore you cannot understand what the song is. Whereas if I'm also singing the words, you'll be able to capture some of those words, and you'll be able to auto-correct some of these words and figure out what the song is, right? So in a that would be analogous to amplitude versus frequency shift keying. So in frequencies, we are adding more information than just the amplitude. So we'll be more resilient to interference from others as opposed to just amplitude variations. So with frequency shift keying operating with a narrow bandwidth was considered a feasible option for increasing the range of communication. So I'm speaking with two different frequencies for bit 0 and 1. And the receiver, even if they are far away from me, if they can tune in exactly to the two frequencies that we've agreed upon, they might still be able to listen to me at a long distance. And particularly something called narrowband FSK became quite popular for long range communication. And again, we didn't get to spend a lot of time on bandwidth, but let's take it as a fact for now that when your bandwidth is lower, you will be able to send to a much longer distance. So if I reduce my bandwidth, I should be able to send over a long range. But what is the downside of reducing bandwidth based on what we spoke recently? If I reduce my bandwidth, the range of frequencies is limited, right? So how will that affect my data rate? Does anyone have a thought on that? So just to recap, narrow band, so the range of frequencies, if we reduce it lower and lower, we'll be able to reach longer and longer distances. So that's preferable. But if I reduce my bandwidth, that's going to reduce the number of frequencies, unique frequencies that I can send. And how will that affect my data rate? Or how will that affect the number of bits that I can send in a given duration?
That reduces.
That reduces. And why does that reduce?
Because we have a less number of frequencies to work with.
Exactly. So we have narrow bandwidth and therefore fewer frequencies to send, and therefore fewer bits can be mapped to those frequencies uniquely. So when we go to narrow bandwidths, we can reach long distances, but we cannot send more and more data. So that's the major trade-off with narrowband FSK and range of communication. And that's a fundamental trade-off, which is if I have to go longer distances, I have to, again, think of our own communication, right? When we hear, if you guys have watched Finding Dory and Finding Nemo, you might have heard whale language. Of course, that's something made up in the cartoon, but a whale language is where you're speaking at a much lower frequency. And when you're speaking at a lower frequency and the range of frequencies are limited, you are able to reach longer distances. But when your range of frequencies are limited, you can only speak slowly, and therefore you cannot convey a lot of information in a given span of time. So the rate at which I can speak and the rate at which I can send information is going to be much lower than the rate at which you can send at a shorter distance. So that fundamental trade-off of long range and lower data rate comes from their relation to this bandwidth, one parameter. And one more factor comes into this picture, which is energy of communication. So in wireless or any radio module, if you have experienced your phone's battery drain when you're on your Wi-Fi, when you are connected to a wireless system, connected to any radio for that matter, it drains much faster than you turn off and put it in airplane mode, right? One of the reasons for that is your radio consumes a lot of power. And anytime your radio is on, you're going to consume energy. So the downside of me speaking slow or the transmitter sending at a low speed is that to send the same amount of information, I have to be speaking for a long enough time to complete that message. If I was speaking faster, I would have finished that at an earlier time. So if I were to complete my communication over a long time, I have to keep my radio on for a long time. And that's going to consume a lot of energy. So not only are we compromising the rate at which we are sending, we also are compromising on the energy consumption or the battery life of the transmitter. So remember, all of this started with us wanting to communicate over long distances in outdoor scenarios such as farms or large cities, where we want sensors deployed over a wide area and we want to collect from all the data from all of them. So if it's deployed in remote areas, we may not expect to have a continuous power source in a field, right? So we started with the cost of solar panels being high, and we want to reduce that cost. So we want to be operating on a battery whose energy is limited. So if our transmitter, in order to communicate over long distance, is speaking slow and is draining a lot of energy, the battery life is going to go down. So we have a trade-off here, which is I can only send limited data. And if I'm sending that data more often, my radio has to be on for a long time, and that's going to drain my energy. So this low power wide area network technologies came to be a research question because of these trade-offs, that if I want to go long range, I have to speak slow. But if I speak slow, my energy is going to increase. And if my energy increases, my battery life will decrease. And the third problem would be that if there are many devices that are speaking simultaneously, let's say there are 10 of us in this room and each of us have something to say. If all of us speak fast, in 1 minute, if we are all given 1 minute total for all of us to share information, and we all convey our thought in 10 seconds, we all convey our thought in 5 seconds, let's say, all of us can still be able to communicate all our thoughts and be done within 1 minute. Whereas each of us, if we ended up taking 20 seconds, we can not all of us can complete our thoughts, right? And even worse, if we don't see each other and if we randomly say what we want to say, we might be overlapping each other's thoughts, or we might be interfering with each other's communication. And that's exactly what happens in low power wide area networks. When you have more and more devices, each of them are speaking slow, they are going to take a lot of time to say their information. At the same time, someone else might want to send their data, and these two will collide, and these two will interfere, and the receiver will understand neither of them. So one of the reasons then, one of the questions then we have to ask is there a modulation that can allow devices with this limited bandwidth to send their information over a long range, but be able to coexist with each other and send at a relatively faster rate? And this is where something called Chirp spread spectrum came into picture. If you haven't taken any communication course, or if you're planning to do communication, you might learn the term spread spectrum communication in the future. And some of the cellular networks, some of the technologies use something called code division multiplexes. How many of us have heard the term CDMA? Even if it's not in your course, CDMA might be something you might have heard in your cellular network company advertising. I see some hands-on familiarity to CDMA. So was that in the context of communication or in the context of a product advertising CDMA? Those who raise their hands, so maybe Aishwarya, can you tell me how you're familiar with CDMA? Communication networks, you studied about that in classes, is it? Okay, that's good. So in many of these spread spectrum communication, the intent is that I'm going to use a range of frequencies simultaneously and still be able to coexist with others. So, and that's where this concept of chirp spread spectrum came into picture. So it was built on top of, or it was a variation of frequency shifting, or I would say they're cousins of each other. They have some similarities, but quite a lot of differences that lets frequency chirp spread spectrum perform better than frequency shifting in such low power wide area networks. And chirp spread spectrum as a technology, although has existed for a long time, in fact, a lot of I think sea animals and birds use chirps as a way to localize themselves. So they would send a chirp signal. If you, the word chirp comes from birds chirping. So birds chirp, and a chirp is reflected by the neighboring buildings or trees and others. And based on the time it takes for this chirp to come back, they'll try and localize themselves. I'm a big fan of, by the way, Finding Nemo Dory series. So I'll come back to that reference once again. In Finding Dory, one of the, I think, beluga whales, it tries to localize itself by sending acoustic signals, right? And beluga whales use chirp signals to localize themselves. They send chirps over the air, over water, and based on the time of flight, time it takes for the chirp signal for it to come back, it estimates how long an object is from that. In fact, it could also estimate how large an object based on the amplitude of the reflected signal. But coming back to communication, so chirp spread spectrum is something that's present in nature for millions of years. And even in communication, radar has used chirp spread spectrum for localization. But CSS, I'm going to use CSS from now on. CSS is a way to send information rather than localizing, was popularized by a company called Semtech, and they came up with this technology called LoRa. LoRa stands for long range, LORA. So they use chirp spread spectrum to reach long distance of communication and coexist with multiple devices. So this figure is really a good comparison between FSK and chirp spread spectrum. So let's look at what chirp is. I've been saying the term chirp quite a lot. Let's look at what that is. So if you've heard birds chirping, you might have seen that the frequency of that is going to increase with time. Seeing a chat message. Thanks, Shata. Yeah, so in...
somebody has raised the hand.
I see. Sai
Krishnan.
Krishnan, is it? Did you have a question, Sai? Okay, I think it's maybe something.
Forgot to yeah.
Yeah, that's possible. Okay. Okay, yeah. So a chirp is something where we increase the frequency of your signal as a function of time. So just remember a few minutes ago, we talked about the symbol duration, right? So in a frequency shift keying signal, what did we do? We decided on a time period for a symbol. And throughout that time, we sent a single frequency. If I sent F1, I know it was frequency that correspond to 4 bits in this example, because I'm thinking of 16 frequencies. If I sent F2, it was a different 4 bits. But what we should note down here is that this entire duration T, we're going to send a single frequency F. And that's where chirp and FSK are going to differ from each other. So for the same duration, for the same amount of time, a chirp is something that uses all 16 frequencies to send information, meaning it'll increase from a frequency 0, goes to a frequency 1, 2, 3, 4, all the way to 16. So if you were to, if you guys have used MATLAB and you're familiar with MATLAB, you can play around with a MATLAB function called Chirp. I think Signal Processing Toolbox should let you use Chirp in that. And if you're familiar with MATLAB, but you don't have Signal Processing Toolbox, that's okay. You can still look up Chirp help, and it has a lot of functions to generate a chirp. And you can even play it on your audio output, any of your audio output, and listen to that chirp. So it'll just sound like boo, and with every time instant, your frequency is increasing. So suddenly your pitch is increasing all the way to the top. So imagine someone singing and their pitch goes from lower to the higher most, right? So if they're going from their bass voice to their high pitch, then you'll see that transition happening really fast. And that's exactly what a chirp would sound like. So if I have 16 frequencies at my disposal, a frequency shift keying modulation would map each of those frequencies to a unique bit sequence, whereas a chirp would use all the frequencies. It just goes from F0 to F16 in that given time T. So if my symbol duration is TS, I'm going to quickly take 16 steps to reach these 16 frequencies. So how will, in frequency shifting, we were able to match a frequency to a bit sequence, right? So how will we match something like that in Chirp if we are using all 16 frequencies at the same time? We need unique ways of mapping bits to an EM signal, right? So here we're saying with time, my frequencies are going to increase, but I don't know how to differentiate between bit 1 and bit 0 and bit 00 and 01 and so on. So that's where modulation comes in. So how can we modulate such a chirp signal? And this is where some of the core properties of chirp spread spectrum are leveraged. And we won't go into that, but what is interesting about chirp is that if you take this chirp and instead of starting at F0, let's say you started at F2, so or F1, it looks something like this. Your chirp is still going from 0 to all the way to F16. If it comes back 0 and then F again, that is also a chirp. Meaning if I take a chirp going from F0 to F16, I start at a different frequency. I go all the way up, come back, and then back to F1. That is a unique chirp. So let's say I started with F2. I can go all the way to bandwidth, come back, and F2. So my receiver can differentiate between these two chirp signals. And we'll not see how I'm able to differentiate this. That's something I can point you guys to a different material if it's of interest to you. But let's take it now that with different starting frequencies, I can still see them all as unique chirp. So if I have 16 frequencies in FSK, I was able to map to 4 bits. So if I tell you that I have 16 frequencies, I can use each of these 16 frequencies as a starting frequency, right? So how many unique chirps can I generate with the 16 frequencies in hand?
16.
16. Why is that? You have each starting frequency can be one of the unique frequencies with us, right? So that is how now chirp spread spectrum can be used as a modulation, in that I am going to use all 16 frequencies all the time. So if you look at this chirp in time duration 0 to TS, it is using frequency F1, F2, F3, F4, F5, all the way to 16, back to 0, and then F1. Similarly, F2, I'm going to use all the frequencies to F16, back to F2. So I am going to use all frequencies at my disposal, but because I have figured out a way to let my receiver, that I started with this unique frequency of F1, F2, F3, F4, and so on, I'm able to map each of these frequencies to a particular message. So now there are 16 unique chirps that I have. Each of these can be mapped to a bit sequence. So all frequencies are being used, and still I could map 4 bits to a particular frequency, to a particular chirp signal, right? So I can still send 4 bits in the same duration, just like FSK. So I've not gained anything by using this chirp when it comes to packing bits into a particular duration. But what I've gained is that because I'm using all frequencies all the time, I am more resilient to any interference from external factors. So say you are sending this frequency F2. Once again, I do want to remind everyone that when we think of frequency shifting and how we implement, this is a much simplified version of understanding it. It's not exactly how it's done. But let's say I'm sending a particular frequency F2 to convey bits 0010. So that bit sequence of 0010 corresponds to F2. And if someone else is also sending something at this frequency F2, even if they send for a short period, let's say over here and over here, that's going to interfere with my message, and I lose all my bits of 1101. At the same time, if we go back to this chirp, if say at this point someone was interfering, first of all, in order for someone to interfere with me, they'll also have to follow the same step sizes, right? If say someone is interfering with me at this frequency, F1, they might only interfere for a short period of time, because the next step, I've gone to a different frequency altogether. So just like what we talked about earlier when it comes to say, singing with the words, right? Even if 2 people are singing, even if you miss one word from the first person song, when the other person is speaking, you are able to understand the rest of the song, because you know how that song goes. So you know how this progression is going. And because of that, you're able to correct for some of those lost interferers. So I've marked in this case a interferer at F2. In case of FSK, even if this interference was present for a short period, that's going to affect my entire message. Whereas in chirp spread spectrum, if someone in particular frequency is interfering with me, they'll only affect me in this short period. The rest of the progression is not affected, and therefore I'll be able to recreate what was sent me as a receiver and still demodulate that message. So this resilience to interference would it gives chirp spread spectrum an upper hand over frequency shifting. And LoRa as a technology has used chirp spread spectrum quite efficiently to reach longer and longer distances of communication. And there are a lot of open challenges in implementing this, in demodulating and analyzing this, but it's a great start to increasing the range of communication without compromising on this interference and multiple devices coexisting. So chirp still has the same issues that we talked about earlier, which is if I still have to send, remember we did not change the number of bits we can send in the same duration. We've only made it more resilient. So the number of bits I can send in a duration remains the same, and therefore my the speed at which I can send my message is going to be the same as FSK. The energy drain is going to be the same as FSK. Because now we've made it more resilient, we might be able to send to an even longer distance than FSK could do. So I was able to increase distance by being more resilient to interference. And there are some factors that affect the configuration of a chirp. So the number of steps, the first aspect is the bandwidth, which is the range of frequencies, just like FSK. The maximum range of frequencies that I can have would be defined by bandwidth. So if I have 16 frequencies, my bandwidth would be the maximum frequency that I have, which is F16. So if I want to send more and more bits per chirp, I have to have a larger and larger bandwidth. Or another way of packing more bits is to have more steps in the same duration, right? So if I have only F16, 16 messages, and although I have the maximum number of steps I can take is F16, so that's the maximum data rate, but I could take it even slower than that. So let's say for 2 units of time, I'm going to be at one frequency. Instead of using all the bandwidth, I could pick only odd frequencies to use or only even frequencies to use. So I could go lower on the number of steps that I take, and that could make me that could make my data rate come down, but that'll be less resilience, but I would be able to send more bits per in the same duration. And we'll not have time to talk about why that's the case, but if you guys are interested in knowing how we can pack more bits per chirp, I can send you some pointers to that. And some of the questions in our quiz is about some of these parameters, so that I'll just mention that one parameter, which is called spreading factor. So spreading factor essentially is, is the 2 power of that spreading factor is the number of steps one can take in a particular chirp. So if we had, say, 4 bits for 16 frequencies, the equivalent of those 4 bits per symbol would be spreading factor here. So if I have 16 frequencies and I can take a maximum of 16 steps here, then my spreading factor would be 4, because I've logged to the base 2 of 16 is what I'm looking for as spreading factor. So the 2 parameters of spreading factor and bandwidth helps me play around a little bit on the range of communication, how much resilience I can add, and how fast I can send this information. So some of the questions that I have, I think I was a bit more optimistic when it comes to talking about LoRa. So I don't think the last 3 questions you can, 3 or 4 questions you can answer, because they've not gone into detail of that. But if this is of interest to you, certainly ping me. I can point you to resources, or we can have one-on-one chat after this as well. But I think I'll stop here and maybe have time for a few questions in the next 2 minutes if anyone has any. I could, so I'm going to send one link here, which is some intro to LoRa, which can be a good starting point.
Thank you, Bhuvana. Can I ask a question, please?
Oh, sure, yeah.
So just curious, I mean, when you see about LoRa or these kinds of low power technologies, it seems to be an open source standard or something like that. So as a software person or coming from this side, I was wondering, I mean, when we see cellular networks, we see big companies that have come up with ideas and algorithms and so on. Is there any with these newer technologies, is there any scope or is there any possibility for open source hardware or collaborative design in universities and so on where the control is not at private corporations?
Oh, that's an excellent point, and ties very well with some of the research that's going on in my group. So LoRa, when it first came, like you mentioned, it was similar to cellular in that they did not release their, they did not open source their transmitter or receiver design. And quite a few companies reverse engineered their design. And initial LoRa research worked on many assumptions and using black boxes. But now we've come to a mature enough stage of open source transmitter and receiver design. So LoRa's white sheet has given a lot of, white paper has given a lot of information, and data sheets and white papers are quite open for us to understand exactly how it's implemented on the transmitter and receiver. And that has triggered a lot of systems research in implementing LoRa on software. So when it comes to communication devices, quite a few technologies, people are able to work on them on the basic physical layer because of something called software-defined radios. So software-defined radios gives you access to every single thing that our radio would see. And we can write any program on that and implement everything on the software. So the software-defined radios called USRPs, RPL, SDRs, there are a number of LoRa transmitter receiver designs to be implemented that can be implemented on these software-defined radios. And some of the research that went on in my group were to study if multiple LoRa transmitters sent together, can we still demodulate all that information? And that was done with the help of these software-defined radios, where we looked at the physical layer samples and demodulated everything ourselves. So there's an active line of work and quite a bit of open source software and hardware resources available for recreating LoRa transmit and receive. And I think many of the research community does not fully rely on the hardware, copyrighted hardware to perform research. So they build their own transmit receive design to analyze things.
That's pretty cool. Thank you. Thank you, Bhuvana.
Thanks, everyone. I think if you have questions or anything that could come up later, feel free to email me at bhuvana@ec.vis.edu. And I sent a link in our chat now, which is about LoRa modulation basics, white paper from Semtech, which is a company who came up with LoRa. You can get started on that if this is of interest to you. And I look forward to seeing you all sometime when you're in grad school or when I'm visiting CEG the next time.
Thank you, Bhuvana. Thank you so much.
See you then.